But Dutch physicist Christian Huygens proposed in 1678 that light is a wave rather than a stream of particles. Of course, that was way before electromagnetic theories were developed. And at that time, people did not really take notice of Huygens' light wave theory. However, his theory was later vindicated and has remained useful today. Huygens' principle states that all points on a wavefront are point sources of secondary wavelets that propagate in the forward direction. The new wavefront is the surface tangent to those secondary wavelets. For example, for this spherical wave traveling outward, we can say that every point on this wavefront is a new wave source, producing wavelets traveling outward. It can be proven mathematically that the superposition sum of all these wavelets equal to the original wave. And the original wave front is the surface tangent to those secondary wavelets. If you remember, a wave front includes all the points on a wave crest. Since wave crest means the medium is not at the equilibrium position, when I create a disturbance, my motion is just like bringing the medium to the crest. So it makes sense to say that a wave crest is like a new source of disturbance, a new wave source. Huygens' principle can successfully explain the laws of reflection and refraction, and it is particularly useful for understanding diffraction and interference. For example, when this plane wave traveling to the right hits this obstacle, we can say that every point on this wavefront is a new wave source. So the wavelets travel forward, and that's why we end up with a wave that can reach behind the obstacle. As for this plane wave reaching a small gap over here, this point on the wavefront produces a new wavelet, and this new wavelet is the new wave that gets through and spreads to reach behind the obstacle. The first major convincing evidence for the wave nature of light was English scientist Thomas Young's double-slit interference experiment in 1801. Young used some very narrow slits for his experiment. One classic way to make very narrow slits is to paint a small pane of glass black, and then use a sharp razor blade to cut away a line of paint to form a single slit like this one. For double slits, one can get a pair of razor blades, pinch them together to scratch the paint off, so we can get pairs of double slits like those. Thomas Young shone sunlight at a single slit first, and then a set of double slits. If light is made of particles, the light particles will go through here and here, and so on the screen we would see two bright lines, one here, one there. However, Thomas Young saw evenly spaced bright and dark fringes on the screen like these. This means light does reach behind the obstacle. We usually see shadows behind obstacles because light waves have very short, less than 1 micrometer wavelength. So normal obstacles are too big for light to diffract around. And that's why Thomas Young had to use very narrow slits to observe the wave properties of light. Because light rays from the sun are parallel rays, the sunlight comes in as plane waves. After the first slit, we get this circular wavelet. When the wavelet hits the double slit, we get two circular wavelets. And these two wavelets interfere to give us these bright and dark fringes on the screen. Here I have two sets of circular wavelets. I'm going to put them side by side to show you their interference pattern. Right now it is like one slit is here, the other slit is there. As you can see, when the slit distance is much bigger than the wavelength, it is not easy to see a clear pattern. But watch what happens when I move the two slits closer. Now you're starting to see some interference patterns. As the slit distance decreases, the pattern on the screen gets wider, farther apart. Over here, we have black overlapping with black, white overlapping with white. That means peak overlapping with peak, trough overlapping with trough. So we get a constructive interference. So on the screen, this will give us a bright fringe. Over here, white is overlapping with black. So that means the peak overlapping with trough, we get destructive interference. So this is what gives us a dark fringe. If this is the screen, on the screen we would see bright, dark, bright, dark, bright, dark fringes. If I continue to decrease the distance between the slits, so you can see the pattern on the screen will get even wider, farther apart. In this lesson, I'm not going to show you the double slit interference pattern produced by light, but I have a tuning fork here and it is 512 Hz. If I strike the tuning fork, both tines will be vibrating, sort of like two waves coming out from the two slits. So I get two circular waves from the two tines and they will interfere. If you remember this equation, V equals to frequency times lambda. The speed of sound in air is 343. The frequency of this tuning fork is 512 Hz. That means the wavelength of this sound wave would be 0.67 meters. And the distance between the slits, in this case, it is about 1.4 centimeters. So the distance between the slits will be 0.014 meter, which is much smaller than the wavelength. So it is like the two slits are really close together. So if I keep moving them closer and closer and closer, we still get the interference pattern, but they're really wide. So I'm going to have loud sound and a quieter sound, loud and quieter sound, like that. What I'm going to do is I'm going to strike the tuning fork, and then I'm going to rotate the tuning fork in front of the microphone. And hopefully you can hear the volume variation as I turn the tuning fork. And you should hear the volume changing from louder to softer, and then back louder and then softer. Now let's derive some equations we can use to analyze double slit interference. Here we have a set of double slits. The distance between the two slits is d. That's the screen. The screen is a distance L to the slits. And the L is much, much bigger than the distance between the slits, d. I did not really draw the d to be much, much smaller than L, so it is easier for us to see those angles and lines in this figure. The y here is the distance to the center of the screen. Let's say we want to find out whether we get a bright fringe or a dark fringe, a distance y from the center of the screen. To figure out whether we have a bright fringe, constructive interference, or a dark fringe, destructive interference, we need to look at the light rays from these two slits. This light ray travels to this spot, and this light ray travels to this spot, and this one certainly has a longer distance to travel. Now this extra distance is what we call path difference. So what we're going to do is we're going to figure out what that path difference is. If this angle is theta, then this slim angle right here is also theta, because we have similar triangles. This right triangle and that right triangle, they are similar. Because this line from the point on the screen to the center between the two slits, this line is perpendicular to that dotted line. And this line to the center of the screen is perpendicular to this line right here. That's why these two angles must be equal, because over here we have 90 degrees, 90 degrees. Therefore, the path difference, which is this distance right over here, this is the extra distance this light ray has to travel compared to that light ray. This is the path difference, and the path difference will be the hypotenuse d times sine theta, because this side is opposite to the angle. So the path difference is d times sine theta. When the path difference is a whole number times the wavelength, we get constructive interference. Because if we have two waves over here and this wave is one whole wave behind the other wave, we will still have peak meeting peak, trough meeting trough for constructive interference. And so the m can be 0, 1, 2, 3, whole number. And this m is what we call the order number. If d sine theta equals to half numbers times the wavelength, then we are going to have peak meeting trough, and we get destructive interference, which means on the screen we would see dark fringes. In order for these calculations to work, the phase relationship between the two waves from the two slits has to be fixed. By that I mean, for example, when the peak of the light reaches this slit, the light reaching the other slit has to be a peak as well. Actually, they don't have to both be peaks. They can have a phase difference, but that phase difference has to be a constant, not changing with time. Because of this, we need our light sources to be coherent sources. So for double slit interference, we need coherent sources to produce the interference pattern. And the coherent sources produce waves with the same wavelengths and bear the same phase relationship to each other at all times. An example of coherent source is a laser beam. A laser beam is coherent light source because the light in an entire laser beam has the same phase. However, sunlight or the light from a light bulb are incoherent. That's why in Thomas Young's experiment, he had to make sunlight go through a single slit first. After that single slit, the wavelet would provide a coherent source for the double slits.